Okay, good afternoon everyone. Let's get started. So today we are going to jump into lecture 7 about neural architecture search. It's a new section. So as a review, we talk about pruning, we talk about quantization, and the pruning lab is due today, so make sure you submit the homework lab 1 by today. And also lab 2 is out about quantization. We'll implement a lot of cool techniques like k-means quantization, linear quantization, derive all the equations by yourself to see the int8 quantization, 4-bit quantization, etc. So both lab 1 and lab 2, make sure you check out EfficientML.ai to see the labs. So we are going to start a new section about neural architecture search. So there is many trade-offs between the efficiency metrics and also the accuracy metrics. So it's very hard to get the best of both worlds. In general, we want a low latency, high accuracy, low energy, and also low storage. But it's very hard to compete to get both. From the latency perspective, usually we want a model to run fast. For example, if you want to make a text-to-image generation, you want to generate image within seconds or milliseconds, hundreds of milliseconds. You don't want to wait for like 10 minutes to generate a single image. And also in a self-driving car, you want to make timely action rather than colliding someone or colliding some objects. So the real time matters a lot. Also for robots, right? Robots interacting with other people and some other stuff, you want a real-time interaction. And also energy is crucial, right? Sometimes we want to run these applications on mobile devices, like running on the phone. And these edge devices are battery constrained, right? You don't want to the application to drain your battery and run out of battery within half a day. So energy matters a lot. Energy also matters for training. In large-scale data centers, the cooling is a big issue, CO2 emission is a big issue, environmental issue, and the accessibility to those large power plants is not easy. We are talking about this megawatts power plant, which is very high power consumption. Storage also matters, right? You don't want the model to be like 70 gigabytes. Which make it very hard to download on the phone. Some of you may want to make a startup in the future, build some AI applications, upload it to Apple Store or Google Play. You don't want the user to download it and join the whole month's quota of their 5G quota on the phone. So storage also matters. But none of this is as important as accuracy. Right? Even if you have very low latency, low energy, low storage, but if the accuracy is poor, it's very hard to attract users to use this AI application. So accuracy certainly is the foundation. That's why we put it on the bottom, is the foundation, right? So when we are optimizing the latency, the energy, the storage, we want to make sure the accuracy doesn't hurt or sometimes even improve. So that's a very complicated process. So today we are going to talk about, rather than compressing an existing model by pruning, quantization, can we design a small, compact, and efficient model to begin with? So that's the motivation for neural architecture search. In order to achieve that, we'll go through the following sections. We'll first talk about these primitive operations and review those classic building blocks. If you're an architect, right, if you're constructing a new building, what are the building blocks? Now we are constructing a neural network architecture. What is the building block? And then we'll talk about neural architecture search. What is the search space? And how do we design the search space? And also how to search. What are the search strategies within that search space? So let's start with primitive operations, which is an overview. First, let's recap the primitive operations, like fully connected layer, the input feature, cin dimension, n is the batch size, cout dimension, which is the output feature. The weight is cin times cout, and there's also a bias. The number of max is just cin times cout. We also learned about convolution layer, 1D convolution and also 2D convolution. The input feature size, Cin times W. And if you have both height and width, that's height and width, that's a 2D scenario, Cin to Cout. And the weight is 4-dimensional. We have the kernel height, kernel width, channel in, channel out. And the way to calculate the MAC is multiplying these 6 terms, Cin, Cout, H and W, KH and KW. We also learned about group convolution layer. So basically turn a fully connected layer divided into several groups such that the number of weights can be divided by G. And similarly, the group convolution's MAC is also reduced by G times compared with the original convolution. We also introduced the depth-wise convolution layer, which is a special case for group convolution where the number of groups equal to the number of channels. So each channel basically interact with only itself, interact with itself. So the number of weights, there's no Cout, Cin equal to Cout. So here it's just KH, KW times C. And also the MAC, we have only these 5 terms rather than Cin times Cout, it's only Cout. And finally, we have the 1x1 convolution where KH and KW, the kernel size is just 1, which basically projects the input dimension from Cin to Cout. Okay? So those are the primitive operations. Using these primitive operations, we can construct the building blocks. Okay? So there is a famous ResI 50 bottleneck block, which consists of 3 layers. A 1x1 layer, followed by a 3x3 convolution, followed by another 1x1 layer. Okay? And there is also a bypass layer connecting the input to the output, such that these 3 layers is basically learning the delta, learning the residual. It has a very special design called bottleneck, which is a very good trade-off between the expressiveness versus the computation complexity. So as we know, 3x3 convolution is pretty expensive. It's 9 ops compared with 1x1, only 1. So we want to first reduce the number of channels here by 4x via this 1x1 convolution, projecting from 2K channels to only 512. From 2K to 512, and then we do 3x3 convolution from 512 to 512. And finally, we'll project it back to 2K using another 1x1 convolution. So that's the start of the design. Okay, so we feed the reduced feature map, not the original feature map, which has 2K channels, but we want to feed the reduced feature map, which has only 512 channels, to the 3x3 convolution. Finally, we expanded the channel so that we can have a good expressiveness by having 2K channel in the end. So how to calculate the total number of MACs? So the first layer, we have 2K input, 512 output channel, H by W, 1x1. The middle, we have 3x3 convolution, input, output, 512 by 512, H by W times 9, since it's 3x3 convolution. Last layer, from 512 to 2K, 1x1 convolution, and H by W. So that's the total amount of MACs. How does that compare with if we have only the 3x3 convolution? It'll be like this, right? If we only have this 3x3 convolution, each kernel is 9, and then we're projecting from 2K to 2K, okay, from 2K to 2K, that's actually 8.5 times more compared with our case to do this bottleneck architecture, right? So the bottleneck architecture really shrinked the number of channels for the 3x3 convolution, such that we can reduce the max. What about the number of parameters? 3x3 conv, 1x1 conv, which is 2K by 512, and then 3x3 conv, 512 by 512, and then 1x1. So this is the total number of max. And again, compared with just using a single 3x3 conv from from 2k to 2k, that will cause 2k by 2k by 9, which is 8.5 times higher compared with this bottleneck architecture. So the bottleneck architecture in Resident 50 is quite efficient with respect to both the number of max and also the number of parameters. Okay, and after ResNet, there's ResNext, the next version of ResNet, which introduced the group convolution. So originally, we have, this is 256 dimension input, 256 dimension output. We have 1 by 1, projecting from 256, reduce it to 128, and using the 3 by 3 to project 128 to 128. Here, actually, they are using a group convolution with group size of 32. Okay, what does that mean? So we can have 32, it's like we have 32 independent, smaller convolutions. Each one is no longer 128 by 128, but it's actually from 256. Actually project from 256 to 4, okay? Rather than from 256 to 128, we have from 256 to 4. And we have 32 of them, so 4 times 32, that's 128. And we can further change that, since the last layer from 128 to 56 can be also viewed as from 4 to 256, and we have 32 of them. Since 4 times 32 equals to 128, such that we can think about it as altogether we have 32 paths, right? And these paths can work together as equivalent to a multi-path block, and potentially we can convert it into a mixture of expert. So that's group convolution in ResNext. There is also a very widely used architecture called MobileNet, which we introduced the depth-wise separable block. Okay? So we use that to capture use the depth-wise convolution to capture the spatial information, and also use the 1-by-1 convolution to capture the information across the channels. Okay? Why we call it depth-wise separable? We are separating the modeling of the spatial information versus the channel information. The spatial information is modeled by depth-wise convolution, okay? Only spatial information. And then the point-wise convolution models the channel-wise interactions. So we separated them so that we can reduce the computation. What does that look like? Actually, MobileNet v2 introduced this inverted bottleneck block. Okay, inverted bottleneck block. Different from a bottleneck block, actually the number of channels didn't decrease but increased by 6 times, expanded by 6 times. And what is the reason behind that? So here we have depth-wise convolution. And remember, depth-wise convolution, the flops is very low. It has 1 less dimension. Okay, only 5 terms multiplied together. So the expressiveness is very weak. To compensate for that, we want to introduce more channels. So here we are expanding the number of channels by 1 by 1, using 1 by 1 count, expand the number of channels by 6. In the bottleneck layer, we are reducing it by 4, because 3 by 3 normal convolution is very expensive. But here we are expanding it because the depth-wise convolution is very cheap. And we want to have good expressiveness and model capacity. So here we are expanding the number of channels rather than shrinking the number of channels. So how do we calculate the MAC? In this case, 1 by 1 count stays the same, 1 by 1 count, height and width, input channel, output channel, input channel, output channel. Okay? And for the middle part, that's where it gets interesting. So we expanded the number of channels from 160 to 960. Okay? From 160 to 960. Height and width times 9. Since this is a depth-wise convolution, there's no other 960. It's just 960 rather than 960 times 960. Input channel times output channel. Okay, this is depth-wise, so it's just a single 960 in this case. So this is the total amount of max. What about the total number of parameters? Again, using n equal to 160 as an example, I usually want to use real numbers rather than just the ladder so that you can get some intuition. So this is the 1x1 conv, input channel, output channel, 1x1 conv, input channel, output channel. And this is the depth-wise layer, 9 times we have 960 channels. So the number of parameters is very small actually. Just 9 times 960. So that's why MobileNet gets applied to mobile devices a lot. It has very low max and low parameters. And the key reason for that is thanks to this inverted bottleneck layer and depth-wise convolution, where it has one less dimension compared with normal convolution. But it's not perfect. What is under the rug here? So the activation memory is actually not efficient for this kind of inverted bottleneck structure. The activation memory. Why is that the case? Okay, here. You are expanding the number of channels by 6 times to compensate for the depth-wise convolutions, low computation complexity. You're expanding the number of channels by 6 times. So the feature map, originally this big, now is 6 times bigger, right? So it's actually not activation memory friendly. If we look at the inference, this is from Resident 18 to MobileNet V2, shrink by 75%. They are of the similar accuracy of ImageNet. The number of parameters reduced by 4 to 5 times from ResNet to MobileNet. However, the peak activation didn't decrease, but even increased by 80%, right? So the activation is even larger. But you can see the peak activation is not the bottleneck for inference. Okay, this is for inference batch size of 1. Activation is smaller than the weight. However, during training side, where you have a pretty large batch size, the activation matters a lot. So here, the parameter reduced by 4 times, but activation only improved by 10%. Okay, so MobileNet is very good for inference time model size reduction, and flop reduction, but it's not good at reducing the activation memory, which is a bottleneck for training. So at training time, you wouldn't observe much memory reduction if you change from Resident 50 to MobileNet V2 with a very large batch size. All right, next design, next building block, ShuffleNet. Okay. So here we are familiar with this already, 1x1 conv, 3x3, 1x1. And this is group-wise convolution. Now we have three groups. What is the problem here? Different group only interact with itself. Okay, so red group, green, and blue group, they are independent. And now we want to encourage different groups to talk to each other. Okay, therefore, we want to shuffle the channels across different groups. This is after the channel shuffling. The red group have the component from both the red and also the blue and also the green. Okay, so this is the shuffle information to encourage the information to flow between different channels. All right, there's also the transformer building block, which is getting super popular these days, like in Vision transformers. Basically, all the operations are transformer blocks. So for transformer block, there is the multi-head self-attention, MHSA. And what is that? So we have a tensor. We first project it into query key and value with 3 different the projection matrices. After converting that, we pass it through the attention mechanism. We're going to talk about in the transformer lecture in detail, which is basically a scaled dot product between the QKV. We first calculate QK transpose and normalize that by the square root of the hidden dimension. We pass it through the softmax. We do a mask, like a causal mask. Finally, we multiply that with the V, so that every token can attend to every token in this case. If it is causal, the future token or the current token can attend to all the previous tokens. So rather than convolution, which has a very limited receptive field in one layer, you would need a lot of layers, many layers, to have a global access, global receptive field, or a pretty large receptive field. And different from that, this multi-head attention, this attention mechanism, just using one layer, you can attend to all the previous tokens. Okay? Immediately give you a pretty large receptive field, which is good for both vision and also language tasks. So after the MHSA, we concatenate the outputs from different head. So each head, they are independently operating in the attention mechanism, the QK transpose softmax times V. They are doing the attention mechanism independently, and finally we concatenate them together, and then project it again using the output projection matrix. So here, although we have three input projection matrices, like W, Q, K, B, they can be concatenated into a single 3 times larger matrix and do one single kernel call for the matrix multiplication, since we want to avoid the number of kernel calls to reduce the time spent on the GPU kernel calls. So if you see the right-hand side, that basically depicts what is the process of the attention mechanism. We have 3 tensors, QK transpose, and also QK transpose, and also the D. Okay? Q, this is n dimension. We have n number of tokens. Each token is of dimension D. K transpose, that becomes D times n. We do the matrix multiplication. We learn what is the number of max in the matrix multiplication. ND times Dn, okay? And the max is n squared D, n squared D. Since the output is n by n, in order to compute each element, we need D max. So altogether it's n squared D. We do the softmax, and then we do another matrix multiplication with a B. So the dimension would be n times n, so that's the result of nd by dn. The result is n by n. And then we multiply n by n times d. The computation is n squared d. So altogether we have 2n squared d, so it's O n squared. Okay, it grows quadratically with the number of tokens. So as the resolution gets bigger, the number of tokens get longer. As the context gets larger, the document gets larger, the tokens gets larger. This is actually quite computationally expensive. So that's the attention part. And what does the attention map look like? So here is a sentence. This is a real example we have in the HPCA paper called Spaten. The sentence is, I bet the video game is a lot more fun than the film. And we can see the word game attend heavily to video. Okay? And I attend to fun and a lot. And more attend very heavily here to than, since more than nearly talk together. And film here attend heavily to game. Okay? So that's the attention map, capturing the relationship between different tokens. And naturally, you can see some of the tokens, they don't attend to anything. Like pretty much everything is white, so meaning it's not attending to any stuff. So in the future lecture, we are going to talk about token pruning. Tokens like that can be safely pruned. Question?
Why is this not symmetrical on the diagonal?
Why is it symmetric? Why is it not symmetric in the diagonal? It doesn't have to be symmetric. The future attend to the past versus the past attend to the future, not necessarily symmetric. And here, when we are talking about multi-head attention, basically we are concatenating the attention result across different head and pass it through the output transformation matrix, WO. Okay, so that concludes our building block section. Okay, we talk about FC layer, normal convolution, group convolution, depth-wise convolution. We use those convolutions to build building blocks such as inverted bottleneck, and also the multi-head attention blocks. So we have a lot of building blocks now. Now we talk about how do we select among different building blocks. So we introduce neural architecture search. So conventionally, when we are designing the model, we usually design them manually. Okay? There are so many layers, some kernel, we choose across different kernel size, 3 by 3, 1 by 1, 5 by 5, 7 by 7. And we pick a resolution, maybe 224, maybe 256, 384. And we learn those connectivity, bypass layer, no bypass layer. And we want to choose the number of channels, starting with 3. And then we add more channels, gradually add more channels, and reducing the resolution, adding the channel. There is a lot of black magic doing the manual architecture search. And usually it's very hard to get a model exactly fitting the demand of the hardware. For example, Google's TPU has 28, first generation of TPU has 28 megabytes of SRAM, on-chip SRAM. So that fits perfectly with Google 9 V1, okay? Because 28 megabyte exactly can fit the model. Everything can be fit on the cache. But how do we design a model that's exactly 28 megabyte or 100 megabyte or certain size? If it fits, then it can fit in the cache. It'll be very fast. If it doesn't, it'll be very slow. Which motivates us to build automated design space exploration method, so that we can use machine learning to design these neural architectures rather than manually design them. So this is comparing the manual design versus automated design. The search the design space, okay, in this number of max, this is x-axis. We want a low max so that we can make it faster, but we want a high accuracy. So ideally, we want a model that is right here on the top left column. Okay, both low computation and high accuracy. And we hope the circle size to be small. Okay, the circle size indicates the number of parameters. Like this big means it has 2 million parameters. Here is 4 million. Here is 8 million. Here is 64 million parameters. So all these models are handcrafted designs. Like less than 50 is roughly 4 million max. 76 top line accuracy. Exception model ResNet 101. ResNext 101 roughly 80% top line accuracy, 80 billion max. So there's no free lunch. Every increment for the accuracy comes at the cost of the flops. What about automated design? Okay, like this once for all approach designed by our lab, can have only half a billion MAC, but match the accuracy, even higher accuracy compared with ResNext and also exception, which is showing that it's a very powerful tool to use neural architecture search to design a very small model, low computation, but can match the accuracy with the very big human designed models. And this is a whole family of models designed by AutoML. So here you can see the circle in the middle. You can actually distinguish the round is handcrafted versus this asterisk. This is AutoML designed models. And these are AutoML designed models. And you can easily tell the difference between these two. We have a bunch of dots on the top left corner, which is showing that given this huge design space, manual design is sometimes inferior compared with such automated design approach. With that as motivation, let's see what are the components of a neural architecture search, and what is the goal of the neural architecture search. Okay, so given the design space, these are the building blocks. Okay, this is the search space, building blocks, with a lot of building blocks. And then we have a search strategy and also a performance estimation strategy. Okay, we want to propose the architecture and then collect the performance feedback and then iterate this process. If you find a good model, you can stop this iteration. Otherwise, you want to continue this iteration, propose a new architecture, estimate the performance, estimate the efficiency, such as latency, energy, storage, different perspectives, and also accuracy for sure. Give the feedback and repeat the search process again until you find a model and fit your need. And to begin with, let's talk about the search space. Okay, so that's a set of candidate neural architectures we are going to choose from. We'll introduce two search spaces here. One is the cell level, the other is the network level. Okay, so let's first look at the cell level. What does that mean? So this is from the image all the way to the output. We have many layers. Initially, we have a large resolution, like 220, 224, and finally, we have a very low resolution, even a single prediction. So we have to go through many downsample layers to reduce the resolution and input and increase the number of channels. So those are the reduction cell, okay, reducing the number of resolution. Can be done by stratified conv or by pooling. And between those reduction cells, we have those normal cells. Those normal cells are usually repeated. So the philosophy from this cell level search space is that you just want to search one building block, okay, and then you're going to repeat that building block many, many times. Okay, here repeated n times, another n times, another n times, and here for the reduction cell, we are reusing the same reduction cell across different stages. Okay, so basically all the building blocks boil down to two building blocks. One is the normal cell, okay, the normal cell between the reduction cells. Okay? So that makes a very complicated problem much simpler. So previously we have like 50 layers. Now we only need to search 2 layers, and we are repeating these 2 layers for the whole network. These 2 layers fall into 2 categories. One is the reduction cell, one is the normal cell. Normal cell just repeat between these reduction cells, and the reduction cell's responsibility is to reduce the resolution. For example, initially it's 224, and in the end it becomes 7 by 7. Okay, so you reduce from 224 by 224 to 128 by 128, from 128 to 128, 224 by 224 to 112 by 112 to 56 by 56 to 28 by 28, 14 by 14, and finally 7 by 7. Okay, 5 reduction cells. In the middle, that's the normal cell. Let's see the result first, and then we'll go down deeper how that worked. From this paper, neural architecture search paper, the cell architecture is quite unreadable. Okay, so that's the models searched, architecture searched by machine learning. We can see roughly there are this is a layer h, this is h minus I minus 1, so we can take the input either from the previous layer or from the layer before the previous layer. Can do some operation like separable 3 by 3 identity, and then do some operation like add to add these 2 operands, and then concat all the choices together and feed it to the output. And similarly for the reduction cell, basically choose the input either from hi or hi minus 1, pass it through 2 operations, add them together, and then concatenate them in the end. So how is the architecture to select these choices? So here, this paper used a recurrent neural network as a controller to generate the candidate cell. Okay, so we don't quite use R in these days, but let's give a review. At first, select the one hidden state, and then select another hidden state, and then autoregressively select the operation for the first hidden state, and then select the operation for the second hidden state. And now we want to combine these hidden states. We want to select the method to combine these hidden states. okay? And we repeat this b times. So here we first select the gray part, select one hidden state, layer A, and then select another hidden state, so layer B, and then select an operation on top of the first hidden state. Here is select a 3x3 count, and then select the second hidden state operation, which is 2x2 max pool, and then we select the method to combine them, and here is using add operation to combine them. Okay, so we are repeating this process b times. The question here, what is the design space? What is the size of the design space? Say we have two candidate inputs, exactly like this case, and then we have m candidate operations to transform the inputs. Okay, to transform the inputs, the yellow part, we have m candidates, and then we need to combine them. Okay, in the green part, and there are n potential operations to combine them. Add is one of them, but there are n potential methods. What is the size of the search space? So we have b layers. Give you 1 minute to think about it. Hint, consider step by step, which is a very commonly used prompt. Think step by step. So what is the step one? Okay, step one is to select one hidden state. So we can either select from, like we mentioned here, we can either select from the previous state or the state before the previous state. So we have two choices for selecting one hidden state. And then we have another two choices for selecting the second hidden state. And then we select the operation on the first hidden state. There are m operations, m candidate operations to perform the input. And the second one, also m possibilities. And after that, we have n approaches to combine those two hidden states. So that's just one layer. And we want to repeat this for b layers. Okay, so to the power of b. So that's the complexity of selecting the total design space. Assuming m equal to 5, that's actually very typical. We can have 1x1 count, 3x3 count, 5x5 count, identity or pooling. Easily you can get 5 choices. M equal to 5, and then n equal to 2, we can do element-wise addition, or we can do element-wise multiplication. So we can easily have 2 or more than 2 operations for n. Repeating b layers. Given this example, we can have 10 to the power of 11 candidates in the design space. That's a pretty huge design space, which motivates us. In the later part of this lecture, we are going to learn how to select, how to search within such a big search space. Okay, so that is the cell level search space. The philosophy is we took a lot of effort, very big design space, super big design space. We just want to pick a single cell that's very elegant. We want to repeat this cell so many times. But another thinking is that that may not be optimal, because from deeper layer versus shallow layer, you may want different cells. Okay? From the deeper layer versus shallow layer, behavior is very different. It may not be the best solution to just repeat the same building block, same cell across the whole depth of the neural network. Okay? So it might be better to think about the whole design space, the whole network as a whole, as a larger design space. Different blocks may have different architectures. So what is the design space in this case? So starting from the input all the way to the output, we can have a variable number of layers. Okay? Previously, when we are repeating, we assume a certain depth, but now we can also change the depth. For example, the first stage. So here we have 5 stages. Each stage they are of the same resolution. We reduce from 224 all the way to 7. The first stage we can have depths of 1, depths of 2, depth of 3, and similarly for later stage like this stage we can have 3, 5, 7, 9 different depths we can choose from. Also we can have the resolution dimension. Okay, the input resolution doesn't have to be 224 by 224, but rather it can be 128 by 128, or 256 by 256. Or at training time, you can dynamically, randomly select different resolutions, which usually helps. Like in the previous quantization lecture, we learned about usually adding randomness helps with generalization and helps with training. So here we can also train with sometimes with 192 by 192, sometimes train it with 256 by 256. So that's the resolution dimension. We also have this width dimension. Okay, so we can choose from 48 channels in the first place, and the 64 or 96. When we are going deeper, we want to have a larger resolution, a larger dimension right here. So we can have 1280 or 2048, etc. Okay, so we can choose different width. Also, we can choose from different kernel sizes. So different color here mean different different size. For example, here 3 by 3 count, 7 by 7 count, 5 by 5 count. We can have different kernel sizes. It's all very flexible. We can also have the topology, the connection. For example, when we are doing the downsample, from 1 time to 2 times, 4 times, 8 times, all the way to 32 times, we can go through different paths. We can stay at the 8 times downsample and then stay for a while, and then we jump to 16 times downsample until the end. For some super resolution tasks, for some classification tasks, this is the way to go, okay, reducing the resolution. And sometimes for segmentation tasks, we want to have pixel-wise prediction. So the output resolution and input resolution are pretty much the same. So we want to first downsample, then upsample. Okay, so this also applies to autoencoders, which nowadays is very widely used in diffusion models. Okay, LDM latent diffusion models. We are going to learn later in this lecture series. Okay, you first downsample and then you upsample. So you can also downsample, upsample, downsample, upsample. So the trajectory across the grid is representing actually the architecture of the model. Okay, when do you downsample? For example, here when we are doing the downsample, the next layer we are not, and then we are doing the downsample, and next layer we don't. Versus we just downsample, 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 upsample, upsample, upsample. So the different paths, different trajectories within this grid actually correspond to a network architecture in the search space. So that's network level topology connection on the search space. Okay, so now let's take a break before we jump into how to design the search space. All right, welcome back. Let's continue discussion. Let's now talk about design and design search space. So just now we talked about there's a huge design space, right? Either using the cell level or the network level. And how do we narrow down the design space? For example, when we are searching something we don't want to search, like in our forest, the forest is pretty big, so your friend gets lost. The first thing you want to do is to narrow down which part of the forest he got lost. Right? Just like here, we are given a pretty big search space for our target design. You want to first narrow down, okay, your friend get lost in the left part of the forest. Okay, we want to first optimize the search space. And then we do the model architecture search, the specialization within the smaller, the optimized search space. So we'll introduce tiny NAS. How do we do automated search space optimization to search the search space? And then we do the resource constrained model architecture search. We specialize the model for a particular hardware constraint. So talking about hardware constraint, on the mobile devices, the latency matters. You want it to react very fast. The energy matters. You don't want it to drain the battery of your phone very quickly. But on these IoT devices, memory constraint is also a pretty big constraint. And also recently for large language models, memory on the GPU is also a very scarce resource. Sometimes you have only 80 gigabytes of memory. You want to really well utilize the memory. So latency, energy, memory, those are the big constraints. Especially from cloud AI to mobile AI to tiny AI, when we are looking at the memory size, we're talking about tens of gigabytes, a few gigabytes versus a couple of hundred kilobytes for tiny AI, which has a pretty big gap between the available resource of the memory, like a few hundred kilobytes, versus several megabytes for even, not to mention the large language models, which is so big. And if you compare the memory for GPU for mobile phone to microcontroller, it's almost invisible for the microcontroller since the memory is just so small. Here we have 3 orders of magnitude smaller memory and 4 orders of magnitude smaller storage. So as a computer scientist, you want to design across the whole space, both big and also small. That is pretty challenging. So we want to first narrow down a design space. So how do we find a good design space? First of all, here we listed a bunch of design spaces. We have different width, the width of the channel, and also different resolutions, 160, 112, 69, 96, etc. So given these different design spaces, which is good, which is bad? Ideally, we want to evaluate the accuracy by training the model to the end, to observe the accuracy, right? But that is very computationally costly. So how do we evaluate a model without training that? So here we use a very simple but effective heuristic. Is to see a good design space is more likely to achieve high flops under the same memory constraint. You only have this amount of memory. Okay? Give me the most amount of flops. Assuming the model capacity is proportional to the flops. So if given the same model, same memory constraint, you can fit more flops. That is considered a good design space. And also for from hardware perspective, computation is cheap. Data movement, memory access is expensive. So if given the same amount of memory constraints, you can fit more flops. That model architecture is considered more efficient. Therefore, we plotted the relationship between the flops, and also this is the cumulative probability of different design space. Like this red corresponds to a width of 0.5, resolution of 1.4. This black design space corresponds to a width of 0.3, resolution of 160. So it's higher resolution, but smaller width. You don't know which is better, right? Lower resolution, higher width, or higher resolution, lower width. It's hard to tell. But now, in this chart, we can easily tell the difference. So in this red design space, 80% of the models has more than 50.3 million max. But in this black design space, 80% of the models has only 32 million max. So the red design space can fit more flops given the same memory budget. So we consider that as a good design space. We verified that, trained a bunch of models within that design space, and observed that the best accuracy in this design space is about 78.7%, versus in the spec design space only 74%, which verified our idea that a design space that can give you more flops given the same memory constraint will be a better design space. Okay, so we just want to analyze the flop distribution. Larger flops means more larger model capacity, which is more likely to give a higher accuracy. So we use this principle to design this design space. Okay, so, and it's actually quite effective compared with the Resident 18 and 224 resolution, which is actually running out of memory on the microcontroller's design space. Our space is superior compared with even larger, huge design space or random design space. And also the search space with higher mean flops on the x-axis versus the accuracy, they are very positively correlated. Okay, so if you have higher flops, then very likely you have high accuracy. The correlation is similar, is pretty linear. All right, so we use this approach to narrow down a design space using the heuristic that you want to have more flops given the same memory budget. And now let's talk about, now we finalize the design space, how do we do search on top of that design space? And how do we automate this process without human intervention? Which is quite helpful if you want to build a product, build a tool. You don't want to specialize by using a human expert. Okay, that's not scalable. You want to have a push the button solution no matter what kind of scenario came. You're given a new memory constraint, given a new latency constraint, you want to exactly fit this amount of design target, accuracy target, latency target. How do we have a push button solution to find the neural network architecture? So we'll talk about several search strategies on top of the search space, including graded search, random search, reinforcement learning, gradient descent, and also evolutionary search. So let's start with graded search, which is the simplest and sometimes work very well. So graded search, very traditional way of parameter optimization. You can have many degrees of optimization. In this scenario, we use two for illustration purpose. One is the resolution, 1x or 1.2x or 1.1x. The width, either 1.1, 1.2. So we are trading off between resolution and width. We call it grid search because each dimension we can have a step size, and then we can have a grid by dividing the whole space into several smaller ones. Each dot on the grid is one design in the search space. So the entire search space is represented as the Cartesian product of a single dimension design spaces. Like this is basically the outer product between the resolution and the width. And to obtain accuracy on each candidate network, we want to train them from scratch. We don't have to train them all the way to convergence, but we can train it for a while to observe the accuracy. So that's the bad part of it. You have to train for each design. If you have a lot of GPUs, that's probably a very easy way. Just 2 for loops, for resolution, for width, train them, and pick the best one for me. Of course, you want to satisfy the latency constraint. And some of them, if you have very large width, pretty big resolution, you may not fit. You may not satisfy the latency constraint. So we are going to eliminate them even before we train them. Okay? So eliminate the points, the design that break the latency constraint before training them. So this is very easy to implement, but it may take quite a long time to evaluate them one by one. Make sure you prune away those obvious bad ones, like the red ones in this scenario. And now we want to introduce compound scaling. You have so many dimensions to search from. Do you push one to the extreme, or do you tune each knob moderately for each other? Okay. So given this baseline, This is baseline architecture from input to output. We can scale the width, make the width much wider compared with the first one. We can also still scale the depth, make it much deeper. We can also scale the resolution, okay? Higher resolution, lower resolution. And the best way is actually do not corner each design knob to the extreme. Like only scale the width, only scale the depth. But we want to do compound scaling. Okay, that's the lesson here. You want to make it a little deeper, but not absolutely to the extreme. A little higher resolution, a little wider. Okay, so here the target is to make the model 2x as the original network. So you don't want to make only one dimension 2x, but for each dimension, the width, depth, the resolution, multiply them together, you want to have 2x, but not each of them. Okay? So that's the principle. And similarly, if you want to compress a network, you don't want to just do pruning. You don't want to just do quantization or distillation. You want to put them together. Okay? Just do a little bit of each and combine them together. That usually works pretty well. So that's grid search. Okay? Random search seems very trivial, right? You can compare with grid search. One by one, you just for x, for y, and then evaluate each of them. Now you can randomly evaluate them in the design space. But this is actually quite non-trivial and quite helpful for sanity check to start with. Even in the homework, make sure you run random search for a little while. You don't want to see that the reward gets constant, no improvement at all. That must be something wrong in your design space or the search or the evaluation or the reward function. Usually you want to do some first order approximation, do a quick sanity check by running random search. And after a few iterations, you probably want to observe some improvement of the latency accuracy trade-off. So random search, usually the first step to do. Reinforcement learning. That's a very advanced way, some tricky way, and not quite easy to use in practice, but I want to put it here. So you design a sequential decision-making problem. So you want to decide what is the number of filters, what is the filter height, filter width, stripe, height and width, number of filters, and filter height, etc. Okay? You want to design them step by step, one by one, using a RNN. Nowadays, RNN is no longer popular, probably using an autoregressive model, some kind of autoregressive model, not necessarily RNN controller. And using that controller to propose a architecture consisting of the height, the width, filter size, etc. Propose this architecture with probability P, and then train a child network with this architecture to get the accuracy, latency, to get a reward. And then you compute the gradient of P, which is the probability here, and scale it by R to update the controller. So you can have an updated controller, and next iteration is going to encourage high reward and discourage bad reward, and repeat that process as your reward gets higher and higher. We can also use gradient descent to make this search process differentiable. Okay, so for a path from this node to this node, we can have many different choices, many different configurations. We can have here 3x3 count, 5x5 count, or depth-wise count. Okay, so how do we choose from them? We can treat the output as a weighted sum of different edges from different red, yellow, different colors. Right? We are learning the probability of choosing different choices. For example, here we are choosing this blue part. Maybe it could be like 1 by 1 count, right? But actually, during training time, we run inference for all of them. You can imagine the memory requirement would be much larger because we have to run the activation for both the 3x3, 5x5, and 1 by 1. And we are learning the probability for these three. Okay, and with an inference time, we sample the one with the highest probability. So at training time, you can imagine this takes a lot of GPU memory. And inference time, we just pick the one with their probability, sample across according to the probability, and choose a path. And this is about making it differentiable. How about latency? Can we also make latency differentiable? If the case, that'll be interesting, right? So here we have 4 different choices for this layer: 3x3 conv, 5x5 conv, identity, and pooling. Okay. From the accuracy perspective, probably 3x3 and 5x5, maybe 5x5 has higher expressiveness, has higher capacity. But from the latency perspective, they're slow. The identity would be the fastest, right? So how do we take that into account when we are doing the stochastic gradient descent? Previously, we just care about the cross entropy loss, which doesn't factor into the latency. Like identity may be a lot better than 5x5 with respect to the latency. So how do we make latency differentiable? So here we learn the probability of choosing each path in alpha, beta, etc. And then we pre-measure the latency for each building block. Like we pre-measure the latency for the 3x3 convolution, measure the latency since it's the same across different inputs, measure the latency for 5x5, the latency for identity, the latency for pooling, and then the expected latency would be summing up the probability times each latency, probability times latency, probability times each latency. So that's the expected latency, okay, given the probability distribution here. And we can update this probability distribution by adding this expected latency to the loss function. Okay, so this is the cross entropy loss. This is the regularization for the weights. This is the latency portion of the loss function. Okay, in this way, we are learning the probability so that we can make latency differentiable. And we plug in this latency as part of the loss term, so that when we are doing the gradient descent, we can also take care of the latency. Okay, such that we can learn a model that both give a high accuracy and also give a low latency. Any questions about this part? About how to make latency differentiable? Okay, good. The next way to do about the search strategy is about evolutionary search. Okay, a quick review. We talked about starting with random search, right? And then we talk about using RL, gradient search. Now let's talk about evolutionary search. Okay, that mimics the evolution process in biology. We have a population, which is our design space, and then we have a fitness function, which basically is the accuracy, the latency, etc. And then we do mutation crossover. We talk about that. And then select the survivor, assuming they are the best species. And then we repeat this process to do mutation crossover, and then survivor selection, repeat this process on and so on. And then we terminate. So let's see how that works. Fitness selection. We are given a once-for-all network. We're going to talk about in the next lecture and also in the homework. Given a sub-network, we want to measure the latency and accuracy. We want to have low latency and high accuracy. Okay? Otherwise, it doesn't fit. It's too slow or the accuracy is too low, then we need to resample. And after that, we get the feedback, resample again, and repeat this process. So the fitness function is basically selecting between the latency, the accuracy, the efficiency, such as latency, throughput, memory consumption, energy, etc. So that's the fitness function. And what is mutation? Okay, so we started with this network architecture. 2 stages, depths of 3 in the first stage, depths of 3 in the second stage, and then we mutate the depths such that the first stage can become depths of 2, second stage can become depths of 4 or 3 or 5, and we can change it. We can change the depths, we can also change the operator. For example, we mutate from a 3x3 convolution to a 5x5 convolution, from a 3x3 convolution to a 7x7 convolution. So that's mutation. We can also do crossover. So crossover take 2 inputs, mutation take 1 input. Okay, so crossover take 2 inputs. This is input 1, this is input 2, two architectures we want to cross over. So these two are the same, so from parent 1, that's no problem. From the second layer, we can choose from either parent 1 or parent 2. Actually, the crossover is chosen from parent 2. And similarly for the last layer, it's also chosen from parent 2. Okay, so randomly choose one operator among the two choices. We have two parents for each layer. So that's the crossover. We are going to implement that in the third lab, so make sure you are clear about this. About mutation takes one input, crossover takes two inputs, two parents. After that, we conclude this lecture about the math. We first introduced the primitive operations and use that primitive operation to construct the building blocks. And then we talk about the search space, very large search space, cell level versus the network level. And then how do we design the search space such that we can have high flops given the same memory constraint. And finally, how do we search on top of the search space using random search, grid search, reinforcement learning, and evolutionary search. Okay. All right, so lab 2 is out. Feel free to check it out and let us know if you have any questions in the office hours. Here are some references. Thank you. That's all for the lecture.